Electric fields usually vary with distance from the source of the field, the charges. How fast it drops off depends on the shape of the charge distribution making it. The simplest shapes to consider would be a flat sheet, a line of charge, a single point charge, and a pair of positive and negative charges forming an electric dipole. It turns out that the electric field of an infinite sheet of charge is actually constant. Like, it doesn't matter how far away you get from it, the electric field will be the same. There isn't an infinite plane in real life, but to a great approximation, we can take like a small disk or something, and close to it, the field is going to be completely constant. And the field strength is proportional to the charge density. In the case of a line of charge, the field actually drops off with R. So 2k lambda, lambda is the charge per length, over R. The point charge formula is the most basic one. The size of the electric field is kq over r squared, the inverse square law that we're used to both for gravity and electric force. And then finally, the electric dipole, as I've worked out in two other videos, the electric field of the dipole along the sort of equatorial axis is kp over r cubed, and along the dipole axis, it's 2kp over r cubed. And of course, it's slightly more complicated at different angles, but the basic idea is that it drops off as r cubed. So there's a progression. A plane doesn't drop off. A line drops off with r. A point drops off as r squared, and then two sort of combating points drops off roughly as r cubed.